So the idea with this chapter is that rational expressions can be treated like fractions. So I'm just going to go through, I'll start off with some problems in 6.1 where we have to reduce things. And so let's say we've got something like this. So what we want to do is we want to factor things. And this is a difference of squares. So we can write this as y minus 3, y plus 3. And then we want to factor this also. This will be y minus 3 times y minus 3. So in this case, we've got the difference of squares. So we use our form for difference of squares, where the a is y and the b is actually 3. We're squaring 3 to get 9. And so we use the fact that a squared minus b squared is a minus b, a plus b. So that's how we're coming up with this factorization of y squared minus 9. Here, a is y, and b is 3. Now, for this one, again, we have a visible 1 in front of the lead term. Now, we first put this in standard form, so we have highest power of y, next highest power, constant. And then we use the guess and check method. 2 numbers that add up to -6, but multiplied to 9. Well, those 2 numbers are going to be -3. And so that's how we factor those 2 polynomials. Now, this is exactly like factoring fractions. So, for example, if we have, let's say, 6/10, we can give this to 2 times 3. And this one, 2 times 5. And then we cancel the 2's, and we're left with 3/5. So same thing here. We can cancel the y minus 3. And we're left with y plus 3, y minus 3. So this is like reducing fractions. And then in 6.1, we looked at multiplying and dividing rational expressions. And again, we do that the same way we multiply and divide fractions. So I'll do one more from 6.1, then jump to 6.2. So let's say we have something, let's say something like this. So suppose we have something like this. Well, again, we're going to treat these like fractions. So for example, let's say we have 4/7 divided by, let's see, 8/9, something like this. And what we do is we keep the first one, flip the second one, and then we multiply. So keep this one, flip this one, and then we multiply. So we'll get 4 times 9 over 7 times 8. And we might notice that 8 contains 2 times 4. So before we multiply everything together, let's look at the factors and see if we can find something that cancels out. And we do. And so we'll get 9 over 14. So what we do with fractions, again, we're going to do with this. So we'll keep the first one. We're flipping the second one. And now what we would do is just multiply. And we multiply rational expressions the same way we multiply fractions. We would just multiply across. So that's going to give us we're going to get something like this. Now, what we want to do before we try to say take this and distribute it to each of these terms, and if you take this and distribute it to each of these terms, you get really kind of a complicated expression top and bottom. Let's factor things and see if anything's going to cancel out. Now, again, this is a difference of squares, where a is y, b is 5. So y squared minus 5 squared. So that's going to become a minus b, a plus b. Now this one, again, we're going to use guess and check. So 2 numbers that add up to 4, but multiply the negative 5. Now what those 2 numbers can be y plus 5, y minus 1. Now this down here we can factor out a 2. So we get 2 times y minus 1. And then again we'll use guess and check. 2 numbers that add up to 10, multiply the 25. So now we've broken things down into factors. It's like breaking a number down into a product of prime numbers. So we look for things to cancel. Well, let's see. We can cancel y plus 5 and a y plus 5, y plus 5 and a y plus 5, a y minus 1, a y minus 1. And so what we're left with is not much. Just y minus 5 over 2. So that's what we're looking at with these rational expressions. We're treating them like fractions. We're breaking down each of the polynomials into factors. We look for factors that cancel. We multiply and divide the same way we multiply and divide fractions. We reduce these in the same way we reduce fractions. So now we get to the next question, adding and subtracting. So when we add and subtract fractions, and this is section 6.2, as long as we have the same denominators, we're good to go. We're going to add the numerators. And we're going to get 4/5. We keep that common denominator. Now, if we have different denominators, we need to come up with a common denominator. So one way we can do this, let's look at the prime factorization of each denominator. So 12 is 2 times 2 times 3. And 20 is 2 times 2 times 5. Now, we want to turn the 12 and the 20 into the same number. And we're going to do that by making the prime factorizations the same. Now, they're pretty close. 2's and 2's. This one has a 3, but this one has a 5. Now, we don't remove numbers when we do this. We include numbers. So this one needed a times 5. So now this one has all the numbers that this one has. But this one's still short of 3. So it'll be a times 3. What do we get out of this? We get 60. It'll be 60 for both. Now, how do we get 60 from 12? Well, we took what 12 is, 2 times 2 times 3, and we multiplied it by 5. So multiplying 12 by 5 will give us 60. Now we take 20, we have 2 times 2 times 5. That's 20. And if we multiply by 3, then we'll get 60. So to turn 20 into 60, we multiply by 3. So this is what we're going to do. We'll turn 12 into 60 by multiplying by 5. But what we do to the bottom, we have to do to the top, at least with multiplication and division. So if I multiply on the bottom, I have to multiply on the top. Not there yet. So we'll turn 20 into 60 by multiplying by 3. What we did to the bottom, we've got to do to the top. 35 over 60 minus 9 over 60. So now they have the same denominators. Now we can perform the operation. And we're almost done. We want to try to reduce this to lowest terms. Those will cancel. 13 over 30. So when we're dealing with rational expressions, we're going to do exactly the same thing. The difference is, instead of factoring our denominators into prime numbers, we're going to factor them into factors. So let's do a couple examples here. So we have two rational expressions. Now they have the same denominator. So when we do this operation, we treat it exactly like a fraction. We keep this denominator, and then we subtract the numerators. So we're subtracting this entire numerator, not just the 19, the whole thing. Now, what we should do is factor the denominator. It'll help us look for something we can factor out. Now, this is a guess and check because there's that invisible 1 in front of the x squared. So what we want are two numbers that add up to 6, but multiply the negative 7. So what those are going to be there we go. So I don't see anything that can factor just yet. So what I'm going to do, because I don't see anything that's going to factor, I'm going to simplify this top part. Let's see what we get. Now I'm distributing this minus to both of those terms. So combining like terms, -2 and -19, I'll be -21. Bring up the 4x though. Again, keeping things in standard form. So now we have to answer this question. Two numbers that add up to 4, but multiply to -21. Well, so there we go. Now, if you're looking at me saying, well, you seem to be doing this really quick. You know, I don't do it this fast. This is the, let's see, this could be the 6th or 7th semester I've taught this. So what I'm going to say is I've had a lot of practice. And this type of stuff just takes practice. You just become more familiar with the numbers, more familiar with your multiplication tables. So if you find that it's taking you a little bit of time, don't worry. If it helps, you can think of it like this. Two numbers that add up to 4 and multiply to -21. And then experiment with some numbers. So I like to start with the multiplication. So what are the different ways we can multiply numbers to get? Well, 1 times 21. 3 times 7. That's really it. And we got a -21. So that means we'll be dealing with either -1 times 21 or 1 times -21 or -3 times 7 or 3 times -7. So this is what we have to choose from. These are the pairs that multiply well to negative 21. And now we want to ask, if we added those numbers, would they give us 4? Well, if we add these, we'll get 20. If we add these, we'll get negative 20. Add these, we get positive 4. Add these, we get negative 4. So these must be our numbers. Negative 3, positive 7. And I'll say this. It's oftentimes much easier to do math on paper or on a board than it is in our heads. Just saying. Moving on. We can reduce still. We can cancel x plus 7. X minus 3. X minus 4. And then that's going to be our answer. Now let's take a look at a situation where we don't have, let's get a good one here. We don't have the same denominators. Looking for a good one. That one might work. So let's say we have this. All right. Now, in this case, we don't have the same denominators. So what we're going to do is we need to find a common denominator. So we're going to factor these. Now, this one here, there's nothing to factor. It's just x plus 6. So let's factor this one. Well, again, two numbers that add up to 9, but multiply to 18. And there's two numbers that come to mind. X plus 6 and x plus 3. So just like with numbers, we want to make these factorizations the same. X plus 6, x plus 3 is one factorization. The second one is only an x plus 6. What it's missing, so it can look like this one, it needs an x plus 3. So now the factorizations are the same. So this first one, we didn't have to change anything. So we're going to leave this one alone. But the second one, we had to multiply by x plus 3. So what that's going to mean, we're going to multiply bottom and top by x plus 3. And also, I'm going to factor this into the x plus 3 times x plus 6. So we're going to get something like this. Well, now these have the same denominators. So we can combine them with the same common denominator. Now, the reason I want to factor this is when I combine these denominators, I want to keep things factored. Well, they just become the same common denominator. And I'm looking for things that cancel. I don't really see anything yet. So since I don't see anything that can cancel, now I'm going to simplify the top and see what happens. Now, these two factors I'm going to FOIL. I want to keep in mind that I'm subtracting this entire FOIL. So I'm going to put the FOIL results in parentheses. X squared plus 3x minus 4x minus 12. Combine like terms with FOIL. Minus x minus 12 now I'm going to distribute the minus sign. So when you do that, look at x squared minus 6 minus x squared plus x plus 12. So x squared minus x squared, those will cancel out. We've got an x on top here. And then negative 6 plus 12, positive 6. Okay, looks good. Now, what we have is x plus 6 and x plus 6 are going to cancel out. So because it's going to wipe out everything on top, I'm going to put in a times 1. You can always put in a times 1. So now those will cancel. And we're left with 1 over x plus 3. And that's it. So when you're working with trying to come up with these common denominators, you're doing this really the same way you would with numbers. So to get a little bit of practice with that, let's say we have suppose we had these two polynomials as denominators. Let's see here. So we're looking for what's called the LCD. So we're looking for the LCD. So that's what we've been doing. We want to try to find this common denominator. So for these, again, we're just going to factor them. And again, using the guess and check method. So y minus 6, y plus 1. Let's see. Y minus 5, y plus 1. So define the LCD. We want to make these factorizations the same. So this one has a y plus 1, and this one has a y plus 1. So that's covered. Y minus 6, though, is not found here, so we better include it. And remember, when we do LCDs, we always include factors, we never remove them. And then this one here needs that y minus 5. Now the order doesn't matter because addition and multiplication are commutative. So regardless of the order that you do them, you always get the same result. So addition, multiplication, order doesn't matter. Division and subtraction, it does, but that's another story. But we've got it, y minus 6, y minus 6, y minus 5, y minus 5, y plus 1, y plus 1. So the LCD is going to be that. So any questions about that? All right. So I'm going to move on to section 6.3. Now, section 6.3, we're dealing with complex fractions. In complex fractions with, or complex rational expressions, but we're going to deal with them like we would complex fractions. So if you recall seeing things like this, again, we're going to take the denominators, the 5, the 10, the 15, and the 25. We're going to list them out and break them down into factors. So 5, not just factors 5, 10 factors the 2 times 5, 15 factors the 3 times 5, and 25 factors 5 times 5. Now, once again, we want all these factorizations to be the same. So each of these has a 5. Way to go. But this one has 2 5s. So we better make sure the others have 2 5s. Oh, that one's already in. So 2 5s, 2 5s, 2 5s, 2 5s. We're good. Now this one's got a 2. So all the others better have 2s. What's going on here? We got 5s, 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 and 5s. 2, 2, 2, and 2. I mean, it seems to be all right. This one's got a 3. So all the others have to have 3s. And that's going to even things out. So if we multiply each of these together, 5 times 5 times 2 times 3, and just to check, we can multiply for each line. This one, also 150. 150. And 150. So what this means is our lowest common denominator is going to be 150. Now what we're going to do though, we're going to take this 150, multiply top and bottom by 150. And then we'll distribute it to each of these fractions. Now what's going to happen is because we turned each denominator into 150, because we did that, we know that each denominator will divide into 150, canceling it. And the idea here is to get rid of these denominators. They're just a headache. So we can get rid of all the denominators. We're going to be happy. The way we're going to do that, multiply top and bottom by our LCD, distribute that LCD, and then things will cancel, and we're good to go. So we'll distribute the 150. And we're going to get 2/5 times 150, 1/10 times 150. Six 25ths times 150. And this is what we get. Now, what we're going to look for, since we made this 150 using each of these denominators, that means each denominator is going to divide into 150. So 5 goes into 150 30 times. 10 goes into 150 15 times. 25 goes into 150 6 times. And 15 into 150 10 times. So that leaves the 2, the 1, the 6, and the 7, but we've canceled all the denominators. So we have 2 times 30, 1 times 15, 6 times 6, and 7 times 10. So we'll get 60 minus 15 over 36 plus 70, that'll be 45 over 6. And if you break this into factors, you'll get 9 times 5 is 45, or 3 times 3 times 5 is 45. 106 just breaks down to 2 times 53, and this is actually a prime number. I'll break down further. There's nothing to cancel. So at the end, that's going to be our answer. So that's how we do this with fractions. What about doing this with rational expressions? We're going to do exactly the same thing. So let's say we have this. Let me find a good one here. So once again, let's take a look at all the denominators. We have 3, x plus 2, x minus 2, x squared minus 4. Now, x plus 2 doesn't factor. That's just x plus 2. X minus 2 doesn't factor. That's x minus 2. But x squared minus 4, this is really x squared minus 2 squared. A difference of squares, where a is x and b is 2. We'll get a minus b, a plus b. Now, once again, we want to make our factorizations the same. So we have x minus 2, x minus 2. This one needs an x plus 2. Now, this has the x plus 2, but it needs an x minus 2. So our LCD will be x plus 2, x minus 2. So what this means is we'll take x plus 2 times x minus 2, multiply top and bottom by it, distribute, cancel. Now this one, I'm going to factor this out into the x minus 2, x plus 2, that difference of squares. And so now I'm going to distribute. Put this sort of a little off kilter, just to squeeze it in. Oh, I factored this. So let's look for cancellations. Well, x plus 2 will cancel. So that denominator is gone. X minus 2 and x minus 2 will cancel. So that denominator is gone. And then x minus 2, x minus 2, x plus 2, x plus 2. So what are we left with? We have 3 times x minus 2 and Make sure I got the same one. Yeah, 3 times x plus 2. So 3x minus 2 minus 3 times x plus 2. And then 5, and that's it. Because everything else here canceled. So what we're going to do, we're going to distribute these 3's. If we do that, we get 3x minus 6 minus 3x plus 6. Now, in the distribution, you could have distributed the minus also if you wanted to. I'm going to do the number first and then do the sign. So now we'll get 3x minus 6 minus 3x minus 6 over 5. And then these will cancel. We'll get negative 12 over 5, or negative 12/5. So when we do these computations, we do them exactly the same way as we would with complex fractions. Now there's another kind of problem that comes up in this section, and let me go through that one. It has to do with the negative exponents. Let's see. Let's do this. Now, the thing with negative exponents, you want to recall what we do with these. We want to get rid of them. We want to write these without the negative. And we have to do this one of 2 ways. If we have a to the minus n, if you think of that as a to the minus n over 1, and then when we flip it, we don't have to write the minus sign. So if we take this and flip it, we can not put the minus sign in. Or if we have something like this, well, once again, we can flip it. And when we flip it, we don't have to write the minus sign. And anything divided by 1 is itself. So if we flip this, no minus sign. Flip this, no minus sign. So what we're going to do is we're going to flip all these x's. So this will be 8 over x squared, no minus. 2, we flip x to the minus 1 to get x to the 1, or just x. X to the minus 1, again, we flip it under the 10. X squared with a minus, we flip it, put it under the 6. And now we can try to reduce this down. Now again, we look at all the denominators. We have 2 types of denominators here. So we have x, which factors to itself. And then x squared, which is x times x. So to make the factorizations the same, this tells us we have an LCD. We have to multiply this one by x squared, by x to get x squared. So this is our LCD. It's going to be x squared. So that means we're going to multiply top and bottom by x squared. when we distribute, we're going to get this. Now, here, the x squareds will cancel out. In this one, x goes into x squared x amount of times. Same here. X amount of times, x into x squared. And then here the x squareds cancel out. So what we're going to have is 8 minus 2 times x over 10 times x minus 6. Eight minus 2x, 10x minus 6. Now we're not done. We can factor a 2 from the top and bottom. Cancel the 2's. 4 minus x over 5x minus 3. Questions about that? All right. So the last thing, I know we're running out of time for the regular session, so we're going about 11 minutes, so I'm going to continue on in the 6.4, and I want to do monomials and polynomials. I want to do at least 3 problems from this section. I might run a little over time. I'm still recording it though, so if you have to leave at 2:15, go ahead, but I'm still recording this. So the thing about this section, when we're dealing with monomials and polynomials, you want to recall this, that when we're dividing by a single term, we can break things up like this. If we have, excuse me, for dividing, again, by a single term, we'll break it up like this. So what we're going to do is the exact same thing when we have a polynomial model. Now, one of the things we want to keep in mind is our quotient rule. If a to the m over a to the n, we have the same base, is a to the m minus n. We're going to subtract the powers. So, for example, if you have x to the 4th over, say, y to the 5th, x squared, y squared, for the x base, x to the 4 minus 2, for the y base, 5 minus 2. And so we'll get x squared, y cubed. So let's do an example. Let's say we have this. So we have this. But what we're going to do is rewrite this as a fraction or as a ratio. So we're going to write it like this. And then we're going to break this up. Just like we broke up A, B, and C when we added them together, we have each one of those divided by D. So we're going to get check. All right. So now 36 divided by 6 is 6. And this will be x to the 4 minus 3. And then y. Now in this case, since y has the same exponent in both top and bottom, we're just going to cancel. So 18 divided by 6 is, this will be minus 3. Now again, we have x cubed and x cubed. We have the same exponent. We can just cancel those. And then this here will be y to the 2 minus 3. 12 divided by 6 is 2. And this will be x to the 2 minus 3. And then y to the, well, that's the invisible 1. So 1 minus 3. Or 6x to the first. Minus 3 to the negative 1. Minus 2. X to the minus 1. Y to the minus 2. Now x to the 1 is just x. And you have y to the minus 1, so let's flip that y underneath the 3 so we don't have to write the minus. And it's y to the 1, but we have a 1, it's just invisible. And we're going to do the same thing here. You got to flip the x, flip the y squared. So they're both underneath the 2, next to each other. And then this will be our answer. So any questions about that? All right, so I'm going to get into long division. So this will be probably about 20 minutes. I'm going to go over quite a bit. Again, if you have something to do, go do it. I'll post this video and you can just watch the last 20, hopefully not 30 minutes. But if you watch the end of it, the last portion, you'll see these problems. But let's take a look at something. Let's say we have this. We divide 5 into 627. So first off, we say 5 goes into 6 at most one time. Goes in at most once. Then we take this one, we multiply it to the 5 to get 5. So we put that 5 down here. Subtract, we get a 1, bring down a 2. And that's our first cycle of division. This is just long division. Now for the second cycle, 5 goes into 12. At most 2 times. And then 2 times 5, we get 10. Subtract. We'll get 2. Bring down the 7. And that's our second cycle for division. We've got one more cycle. So 27 divided by 5 is at most 5 times. We take 5 times 5, we get 25. Subtract, we have a remainder of 2, but there's nothing else to bring down, so we're done. So our answer is 125, remainder 2, or this is how we typically like to write it, 125 plus the remainder divided by, this is the divisor, this is the dividend, we divide the divisor. Now, a key thing to keep in mind here is we're doing all of our work with this. This is dividing into this, and then it's this, and then it's this, but we're always dividing by this. This is doing all the work. And then we have these cycles. And we went through 3 cycles here to get the work done. We're going to do almost exactly the same way with polynomials. Let me show you. So let's say we have this. So we've got something like this. Now we're going to write it as long division. Now, what's going to be a little bit different is we're still going to work with dividing by the divisor all the time, but we're working only with the lead terms. So we want everything in standard form. Highest power, next highest power, constant. Highest power, constant. We want it in standard form. And then we're going to divide lead terms. So in this case, what we're going to do, we'll do x squared over x. And that's equal to x. And then x times, and when we multiply by the entire divisor. So we get x squared plus 5x. We're going to subtract. X squared minus x squared is 0. 8x minus 5x is 3x. Bring down the plus 15. Oh, and I forgot to put this up here. We have an x in the x column here. That's our first cycle of division. So we divide the lead terms, the result, put that here. Since this is an x term, we put it over the x term. If it was an x squared term, we would put it over here. So let's do this again. Now again, we're working with lead terms. So 3x over x will come out to 3. So over the constant, plus 3. And then we take 3 and we multiply by the divisor. And if we subtract, 3x minus 3x is 0. 15 minus 15 is 0. So we get 0. There's nothing else to bring down. So that's going to be our answer. Questions about that? I'll do at least one more. And then if you have time, I'll go through another one. But I want to get one more that's kind of critical. Let's say we have this. Now, what we're going to do, we're going to put it in long division form. So 2y minus 1. But we want to be careful here. We're missing a y squared term. We're missing a constant term. So we need to insert those. And the way we do that is we call them 0y squared minus 2y plus 0. If we were missing terms over here, we would need to insert those terms as well. And we do it by using 0y squared for this one and then 0. If this was like 2y squared, we would need to insert a plus 0y. But that's something just to keep an eye out for. Sometimes you have to insert those terms. Questions about that? So once we have all the terms, now we can divide. So again, we're going to be working with lead terms. So 6y cubed divided by 2y, that'll be 3y squared. So in the y squared spot, which we had to insert, we get 3y squared. Now we take 3y squared, we multiply it to the entire divisor. And so we'll have 6y cubed minus 3y squared. Now we do our subtraction. 6 minus 6 is 0. All good. You've got to be careful though. Check this one out. 0 minus a negative. You have a double negative here. It's not just minus. It's 0 minus this negative. Double negative becomes a plus. So you get plus 3y squared. Bring down the negative 2y, and that will be our first cycle of division. Next, we take 3y squared. This is now the lead term. Divide by this lead term. So we're going to get 3 halves y. Then we take 3/2 y. We multiply by 2y minus 1. We're going to get 3y squared minus 3/2 y. Just let me check my arithmetic to make sure I didn't make any error. All right, so far so good. So that means we have minus 3/2 y. And this right here will be 3y squared minus 3/2 y. So this minus this will be 0. This will be a double negative. So -2 plus 3/2, well, that's going to be -1/2. Bring down the plus 0. Now we're going to take -1/2 y divided by 2y. It's going to be -1/4. So -1/4. And then -1/4. Times 2y minus 1. Will give us -1/2 y plus 1/4. So when we subtract, we're going to have -1/2 subtract itself. Anytime you subtract yourself, you cancel out. This will be 0. 0 minus 1/4. -1/4. Let me double check something. All right. Double check one more time. Okay. So that means our answer is 3y squared minus 3/2 y minus 1/4 minus, or you can say it like this, you could say plus a -1/4 over the divisor 2y minus 1. So let's see here. Something's off with my arithmetic here. So this would be -1/4 or 2y minus 1. Something's off. I'm sorry. I might have to go back and do something. Let me see. Oh, no, I think we're all right. I think. This looks like, let me check one thing. Let me double check something real quick. I think I might have made a mistake and I didn't see it. Let me double check. double check something real quick. I think I wrote down 2y, and the question actually had a 5y in it. I think that's what's throwing me off. Oh, 6. Yeah, that's what it was. So that is the answer. Yeah, we're good. I wrote down the wrong problem, but we've got the correct answer. So any questions about that? So let me do one more. Let me do another one just for practice sake. Let's say we have something like this. So we're going to put this in long division form. So again, we're doing all the work here with this. We're going to work with Lie terms. So we have x squared times x plus 1, x cubed plus x squared. We'll get 2x squared. Bring down to plus 5x. All right. So that's our first cycle of division. Again, Lie terms. So plus 2x. So now, that's our second cycle of division. Again, Lie terms. Double check that in arithmetic. Okay, so far so good. Oh, plus 3. Not quite so good. Now subtract. We're going to get 1. So we have x squared plus 2x plus 3 plus the remainder 1 over x plus 1. And that's going to be our answer. So that's it for today. Again, this is just the overview. You do have section 6.4, a more drawn out explanation of more examples in the other video. But I just want to kind of do an overview today. If any questions, let me know.